Today is the fourth day. I decided to change the structure of how I do the videos. At the beginning, it was divided in three different steps. First, I was gonna make like a quick recap, then the actual working, and finally a recap of the working. So now I decided to change it in order for me to start working right away. And I believe it's even better because the way I decided to do it's only two parts. The first part is what I did, and the second part is gonna be actual footage of just me doing it. That's it. And I believe in this way it's also better because I have something else to say at the beginning. Because otherwise it's like predicting something that I don't know how much will I work and all of this. So what I did today, um, basically I implemented two different types of approach of computing Bigram. This is very not complicated Bigram. So first one is counting Bigram. So we have names of different people, and we are gonna try to make a model that it's able to make more of these names. And the way it does it, because a bigram, it's for a given character, it's gonna predict a next one. So if we give an E, it's gonna predict M, and then the M is gonna be the input, and it's gonna predict the other M, etc., etc. So how do we do this? The first approach is to do it by frequency. So what we do is first we have we import obviously the names, and we create a dictionary and count all the biograms in our dataset, right? And we add two special characters at the beginning, at the end, but we later change this. So for example, in the first name, which was Emma, the biograms are gonna be we are gonna have 5 biograms if we count these added characters. So we're gonna have the start character and then E. Then we're gonna have E and then M, then M and M, then M and A, and then A and end of character. And that's it. These are gonna be the biograms, and we basically create a dictionary and count for all the names, all the biograms. So for every name in words, we count all the biograms, and that's it. And what we do next is that we transform this into a basically what we do is transform this into a probability distribution. So we have to normalize the count, and with this we can sample the probability distribution and get actual names. So this is what we do. This is how it looks like, the probability distribution. So for this I did so in this previous step there was a dictionary that stored the counts. In this step what I did is like an incidence matrix. So instead of representing it like a hash map, I represented it as a matrix of 27 times 27. 27 because there are 26 letters and one extra, which is gonna be the special character. And for example, so for example, if it's like a lookup table. So if we are given the character, I'm gonna show this. If we're given the as an input the start character or the end character, the probability of the amounts that it appears in the training set and A, it's 4,410, and all of this for other. So this is frequency. So we normalize this to get probabilities, and we sample. This is what is their normalization? So we normalize, and then we sample from this probability distribution, and that's it. With this we can actually get some names, and these are the names. These are really bad, and we apply the same but using a single neuron, and we can prove that this approach is the same, but the implementation is the one that is different. It yields the same results, and it's like a dual interpretation of the same approach, and I'm gonna show it. So at the beginning we do the same, right? And the important thing here is that, okay, we have basically we have the bigrams, right? So for Emma, we have, if we are given an E, we want to project an M. What we can do is we can separate between like a input and output. So we are gonna call this XS and YS. So this is and we're gonna create like two different lists. Then the input, we map them these into numbers. But this is not enough. What we do actually is we do one hot encoding, right? And yeah, we do one hot encoding. Then we implement the neuron, which is basically multiply this, the input times the weights. We initialize the weights as normal distribution, and we apply softmax, right? Because the outputs, we want them to be ensure they are a distribution. And yeah, that's what we do. And we can implement gradient descent into the neural network to update the weights. So if we do this in PyTorch, we just need to specify as true the parameter requires grad for W, which are the weights, and then we update the value of the weights based on the gradient, right? I mean on the opposite direction of the gradient. And that's it. And with that, we get also very similar results. And the dual interpretation is that the matrix W corresponds to of 27 times 27 corresponds to the matrix P that we see here. And that's it. And in the next video, we're gonna implement a paper, which is the like an improved approach of this, which is actually using a multi-layer perceptron. Okay.